Welcome to the demo video of RF Fingerprinting Migration, developed as part of Work Package 5. This demonstration addresses the challenge where changing the receiver typically requires retraining the RF fingerprinting model. To address this, our solution leverages transfer learning to adapt RF fingerprinting to new receivers, enabling seamless authentication with more efficient retraining compared to classical methods, as we will showcase in this demo. This solution will be implemented in the physical layer of robust 6G architecture and validated in Use Case 2, Scenario 3.
In current wireless systems employing RF fingerprinting, each base station individually learns the unique RF signatures of connected devices. This establishes a secure one-to-one match between receiver and transmitter. However, when a device moves to a new base station, retraining the fingerprint model from scratch is usually required, making the process costly, computationally demanding, and time-consuming. Our solution eliminates this extensive retraining by leveraging transfer learning. Instead of starting from scratch, we transfer the pre-trained RF fingerprinting model to new base stations, enabling rapid adaptation using minimal additional data. This significantly reduces retraining costs, computational demands, and adaptation time, ensuring seamless and secure authentication as devices move across base stations. We present an overview of the RF fingerprinting dataset. To create this dataset, we set up a controlled environment with multiple IoT sensors and receivers at varying distances. The specific details of the setup are provided on the screen. We trained our initial RF fingerprinting model using packets from receiver 3 across 3 distances. Testing this source model across all 3 receivers revealed high accuracy for receiver 3 at 92.2%, but significantly lower performance for receivers 1 and 2, highlighting a notable performance drop of approximately 38% when changing receivers. In the second phase, we leveraged adversarial transfer learning by retraining the model with data from receiver 2. As expected with domain adaptation, this slightly reduced accuracy of receiver 3 for target model. However, it notably improved accuracy for receiver 2 to 76% and for receiver 1 to 72%, despite receiver 1 packets not being included in training. This demonstrates effective adaptation across new receivers with minimal retraining. In this demonstration, we simultaneously run 6 instances of our model testing script using tmux. The top 3 panes test the source model, using receivers R03, R02, and R01, respectively. The bottom 3 panes test the target model with the same receivers in the same order. All packets tested are captured simultaneously under identical conditions. The only variable is the receiver. 3 identical packets will be tested across both models and all 3 receivers. The first tested packet is from transmitter 5, at a distance of 0.5 meters, packet number 3149. As expected, the source model correctly identifies this packet with receiver 3 but incorrectly classifies it with receivers 2 and 1. In contrast, the target model correctly classifies the packet with high accuracy across all 3 receivers. The second tested packet is from transmitter 21, at a distance of 1 meter, packet number 2926. Again, the source model shows high accuracy only for receiver 3 and incorrectly classifies the packet for receivers 2 and 1. The target model correctly predicts the transmitter for receiver 2 and receiver 1. The third tested packet is from transmitter 28, at a distance of 1.5 meters, packet number 2749. Consistent with previous results, the source model correctly classifies only receiver 3, with errors for receivers 2 and 1. The target model once again accurately classifies the packet across all receivers, further confirming the effectiveness of our transfer learning approach.
This solution will be integrated within Use Case 2, Scenario 3, and will contribute to Objective 5 by enabling secure and efficient transmitter identification by migrating RF fingerprints among base stations in smart city environments through transfer learning. By eliminating the need for extensive model retraining when receivers change, our approach streamlines RF fingerprinting, significantly enhancing infrastructure safety, sensing integrity, and overall system resilience in modern 6G networks.